Hi there, in today's lesson we're going to be looking at simplifying rational expressions. And there's a couple things we need to start off with if we're talking about rational expressions. And the first thing is, what is a rational expression or a rational function? And really remember the word rational. When we talk about rational numbers, are numbers that can be expressed as fractions. So a rational function or rational expression is a function or an expression that can be expressed as a fraction. Okay, so when we talk about rational functions, we're talking about big giant fractions that involve these polynomials and these variables. It's two polynomials essentially being divided. When we have something like this, we need to identify what are called domain restrictions. Okay, and we've dealt with domain restrictions a little bit in the past when we talked about square root functions. We had to identify domain based on what x could and could not be. And it's the same thing here. For a rational expression, the domain restrictions are the x values that can't be used, okay? And with a rational, that means having a 0 for the denominator, okay? So domain restrictions are the x values that can't be used, that can't be plugged into the function. And for rational functions, those are the values that make the denominator 0. Remember, when I have a fraction, I can't have a 0 in the denominator, all right? So we want to identify the values that make the denominator 0 so that we can avoid using those values, all right? For example, when I look at these, I just want to identify the domain restrictions on these first couple. Domain restrictions, again, values that make the denominator 0. And so think about this for a moment. If I say that the denominator can't be 0, the only way to find out what's going to make the denominator 0 is to kind of disobey that rule and say, all right, x squared plus 4x minus 12 can't equal 0. So I say x squared plus 4x minus 12 equals 0. And now I'm going to solve this thing, all right? So essentially, I'm going to do the opposite of what I'm allowed to do to find out what's going to make this denominator 0. So I set the denominator equal to 0. I'm breaking the rules a little bit. And now I'm going to solve this. And this is a quadratic, so I want to solve by factoring, completing the square of the quadratic formula. This one I'm going to build a bridge. Two numbers that multiply to the negative 12 but add to the positive 4. Going to be a positive 6 and a negative 2. I can use my shortcut on this one because there's a 1 out front. So that means this is going to factor into an x plus 6 and an x minus 2. And now I'm going to set each factor equal to 0. The x plus 6 equals 0. The x minus 2 equals 0. And I solve each. Here I subtract the 6 from each side. Here I'm going to add the 2. So I find out that x equals a negative 6. X equals a positive 2. But now let's backtrack a little bit. These are the things that x cannot equal. So I'm just going to say that, hey, this can't equal this. None of these things can be equal to this. And that's how I'm going to state my domain restrictions. Essentially, I'm going to say, hey, x cannot equal the negative 6 or the positive 2. And I can write it very succinctly like that. Okay? So I say that x cannot equal those things. Make sure that you don't say x equals those things. X cannot equal those things. And that's what the little slash through the equality sign means. It means cannot equal. Okay? Same thing with the next one. Again, I can't have a denominator that equals 0, so the first thing I do is set the denominator equal to 0. Okay, see what I get here. And once again, I'm going to try building a bridge. Two numbers that multiply to a 20 but add to a negative 9 or a negative 4 and a negative 5. Once again, I can use my shortcut because there's a 1 out front. So that factors into an x minus 4 and an x minus 5. And now I set each factor equal to 0. And I solve each. So here I find out that x equals 4. Here I find out that x equals 5. But really, I'm finding out that x cannot equal these things. So for my domain restrictions, I say that x cannot equal a positive 4 or a positive 5. And that's it. All right? If I apply the same thing to the next one, again, I say I cannot have this equal to 0. I'm going to go right to putting it down as cannot equal 0. And now I'm going to solve this by factoring. This is a difference of squares, so it means it factors into an x plus 10 and an x minus 10. Cannot equal 0. And now I set each factor not equal to 0. On the first one, I subtract the 10, so I find out that x cannot equal the negative 10. On the next one, I add the 10 and find out that x cannot equal a positive 10. And by now, hopefully, we're getting really good at factoring and solving by factoring, so we can do these very quickly and efficiently. And I find out that x cannot equal the negative 10 or the positive 10. Or you could write that as a plus or minus 10. Okay? If I do the same thing with the next one, again, I say that the 2x squared plus 9x plus 10 cannot equal 0. From here, I want to factor this thing, so I build a bridge. Two numbers that multiply to the 20 but add to a 9 are a 4 and a 5. This one you cannot use your shortcut on because there's a 2 out front, so you're going to have to split up the middle term and factor by grouping. When you split that up and factor by grouping, I'm not going to show all of that because you should be really good at it by now. But when you do that, you should end up with an x plus 2 and a 2x plus 5 for your two factors. Now we set each factor equal to 0, rather not equal to 0. And we solve each. Here we're subtracting the 2. Here we're subtracting the 5. Let me bring each of those up here. So I get x cannot equal a negative 2. And I get 2x cannot equal a negative 5. And I have to finish solving that second one by dividing by the 2. So I find out that x cannot equal, I've got a negative 5 halves, and I've got a negative 2 for my two restrictions. Okay? So I'm just setting the denominator equal to 0, saying, hey, x cannot equal these things. All right, same thing here. I've got a 3x squared plus 21x cannot equal 0. Right away, I notice a 3 in common here, so I could divide each side by the 3. If I wanted to get rid of it, that gives me an x squared plus 7x cannot equal 0. But now from here, I don't want to build a bridge to nowhere. This is not a trinomial. This is just greatest common factor. I factor out the x. And now I set each factor not equal to 0. So x cannot equal 0. The x plus 7 cannot equal 0. The first one's already solved. The second one, I subtract the 7 from each side. So I find out that x cannot equal a negative 7. So my two restrictions here, I find out that x cannot equal a negative 7 or a 0. In this one, I once again set this not equal to 0. It's a strange way to think of it, which is why we start off just setting it equal to 0. But keep in mind that these are the things that x cannot equal. Right away, I see a greatest common factor of 2, so I can divide off the 2 because it's an equation. It's going to give me an x squared minus 5x minus 24 cannot equal 0. And now I can build a bridge and solve by factoring. Two numbers that multiply to negative 24 but add to a negative 5 or a negative 8 and a positive 3. I can use my shortcut now that I got rid of that 2, so I have a 1 out front. So this factors into an x minus 8 and an x plus 3. And now I set each factor equal to 0 or not equal to 0, as it were. And I solve each. So the two restrictions I get are the positive 8 and the negative 3. Once again, I'm just going to write that nice and succinctly up here. So negative 3 and a positive 8. X cannot equal those values. All right?